Welcome to the vapor compression cycle topic. This is the typical the figure. This is a typical vapor compression cycle. So, meron tayong condenser, expansion device, evaporator, compressor. In between niya ng condenser evaporator is tinatawag na low pressure side sa evaporator and high pressure side sa condenser. So, numbering system, so dito mag-umpisa, papasok sa evaporator kasi ito yung magpapalamig sa room mo. And 2, ito kasi yung output mo dito. Useful output. Okay. Then, 2, 3, 4. Later, makikita natin sa diagram niya. So, most important refrigeration cycle. We start sa Carnot. So, the vapor compression cycle is the most widely used refrigeration cycle in practice. In this cycle, a vapor is compressed, then condensed to a liquid. Compress, condense. Following which the pressure is dropped so that the fluid can evaporate at low pressure. So, ito yan. Nag-drop yung pressure niya, tapos mag-evaporate siya. Bakit low pressure? Kasi kailangan mas mababa ang saturation temperature niya, mas mababa sa room temperature. So, this study progresses from the classical Carnot cycle to the actual cycle. So, ito pag-aralan natin. The modifications of the Carnot cycle are dictated by practical consideration. So, the Carnot cycle is one whose efficiency cannot be exceeded when operating between two given temperatures. The Carnot cycle operating as a heat engine is familiar from the study of thermodynamics. The Carnot heat engine is shown schematically in figure 1A. So this is a Carnot or composition ng power. Yan. So, paligtad ang ano ito 1, 2, 3, 4. Sa kanina, kasi kanina refrigeration. So, 3 to 4, production ng work or power. So, ito yung temperature entropy diagram. This is a box. 1 to 2 is compression. 2 to 3 is heat addition. 3 to 4, compression, turbine, expansion. Then, 4 to 1 is heat rejection. So, the Carnot heat engine receives energy at high level of temperature. Yun yan. Converts a portion of energy into work and discharges the remainder to a heat sink at a low level of temperature. So next, now we go to the Carnot refrigeration cycle. So pinaligtad natin lahat. Tinong bearing, pinaligtad. Then ang 1, 2, 3, 4 sa compressor na. So discuss natin. The Carnot refrigeration cycle performs the reverse effect of the heat engine because it transfers energy from a low level of temperature to a higher level of temperature. The refrigeration cycle requires the addition of external work for its operation. The diagram of the equipment and the temperature entropy diagram of the refrigeration cycle are shown in figure 2A and 2B. So this is the diagram of equipment. Yung mga symbols ng equipment. This one is the TS diagram. So enclosed yan, yung area ng box na yan is the network. Network is standard convention. Ang sign convention is negative. Pero pag sinabi ng work of compressor, pwede mo sabihin na positive. It is considered as compressor work. Kasi hindi ka lang pipiling may motor yan, bibili ka ng negative, anong parang horsepower, negative 2 horsepower kasi compressor yan. Hindi pwede. Kaya absolute value mo na. So sa sign convention, that is negative. So the processes which constitute the cycle are 1 to 2. So from thermo, 1 to 2 compressor is adiabatic compressor. 2 to 3 isothermal rejection of heat. 3 to 4 adiabatic expansion, and 4 to 1 is isothermal addition of heat. All the processes in the Carnot cycle are thermodynamically reversible. Process 1 to 2 and 3 to 4 are consequently isentropic. May mga drawing nyo pala, pag pinadrawing kayo ng diagram, huwag nyo ito i-incline. So, at least cross out ko agad yun. Isentropic means vertical line. Okay? Isothermal is horizontal line. Yung iba kasi, kumaan sa thermo, pag nag-solve ng problem, ang mga figure, nakatarabingi pa. So, pag tabingi ito, so consider wrong na yan. Kasi, yun na sa isothermal. Isothermal dapat parallel sa temperature. Ano, perpendicular. Okay? Pati itong axis niya. Walang drawing na ganyan. Isa ganon. Tapos, basta. Okay lang kung makikita sa pedicure niya talaga tumabingi. Okay yan. Pero kung hindi naman tumabingi, pero yung drawing niya tabingi, so this cross out. Marami yan. Maraming na yung mga napagsak na. So the withdrawal of heat from the low temperature source and passes 4 to 1 is the refrigeration step. It is the entire purpose of the cycle. Yun. Ibig sabihin, ito yung useful output. Kasi ito yung sa air conditioning, sa refrigeration, ito yung kailangan mo. Okay? All the other processes in the cycle function so that the lower temperature energy can be discharged to some convenient high temperature heat sink. Anong convenient high temperature heat sink? Yung environment, yung ambient, yung outdoor. Hindi pwedeng masyadong mataas. Kasi dadaan kang init-init kasi yung condenser ng refrigeration mo. So hindi pwede yan. Kailangan yung tama lang. Tapos iboblow mo siya ng hangin para lumamig. Babalik naman dito. So the Carnot cycle consists of reversible processes which makes its efficiency higher than could be achieved in the actual cycle. A reasonable question is, why discuss the Carnot cycle if it is unattainable, ideal? There are two reasons. One, it serves as a standard of comparison. Two, it provides a convenient guide to the temperatures that should be maintained to achieve maximum effectiveness. So para ma-check mo yung actual mo 60%, pero yung chinek mo sa Carnot cycle 50. So may problema yung computation mo, hindi yung yung process, yung actual measurement. May mali sa computation mo. May mali mga formula, ganun kasi absent. The coefficient of performance. So ito yung performance. Before any evaluation of the performance of a refrigerant can be done, an effectiveness term must be defined. So the index of performance is not efficiency. However, because that term is usually reserved for the ratio of output to input, the ratio of output to input would be misleading applied to a refrigeration system because the output in process 2 to 3 is usually wasted. As a kasi ito yung out. Diba? Injection. So dito naman is baliktad. The concept of the performance index of the refrigeration cycle is the same as efficiency. However, in that it represents the ratio magnitude of desired commodity divided by the magnitude of expenditure. Such that the performance term in the refrigeration cycle is called the coefficient of performance, defined as coefficient of performance as useful refrigeration divided by the network. Magnitude of expenditure is the network kasi ito yung consumption mo, di ba? Yung power consumption. Useful refrigeration, ito yung desired commodity mo, yung air, yung lamig. So the two terms which makes up the coefficient of performance must be in the same units so that the coefficient of performance is dimensionalized. Okay? Now, meron tayong mga tinatawag na EER at saka SEER. So, sa actual na yun, o sa mga advanced topic na yun, kasi dito lang basic pa lang tayo. Ang EER naman as energy efficiency ratio, that is the reciprocal of COP na may unit ng BTU per, parang yung BTU per hour mo, divide mo na ng cooling, divide mo ng power consumption, pero ang watts. Yan. Baliktad naman yun. Ayun same lang pala. Ano pa yung sasabi kong baliktad. Okay. So, same yun kasi useful refrigeration, ang ER, same lang yun, ang COP, ang ano lang nun is useful refrigeration in kung sakaling BTU per hour divided by the power input and watts. Watts or kilowatts. So that is, ang watts pala, that is BTU per hour over watt hour, BTU per watt hour or in kilojoule per watt hour, ang unit ng EER. Okay? Pero kasing tawag din sa reciprocal dito. Now, refrigerant. So ito, na-discuss natin last topic. The working substance in a refrigeration system is called the refrigerant. One of a number of compounds may be used as the refrigerant. So ito yung mga refrigerants natin. Mga gas kasi yan. Bigas. Hap. May content yan. May vapor, may liquid. Now, conditions for highest coefficient of performance. The high coefficient of performance is desirable because it indicates that a given amount of refrigeration requires only a small amount of work. What can be done in the Carnot cycle then to maintain a high coefficient of performance? To answer the question, first we can express the coefficient of performance of the cycle in terms of the temperature that exists in the cycle. So the heat transfer in a reversible process is Q Rev is integral of T times dS. Areas beneath the reversible processes on the temperature entropy diagram therefore represent transfer of heat. Areas shown in figure 3 can be represent the amount of useful refrigeration and the network. So below is the refrigeration and the network is yung nasa box 1, 2, 3, 4. Total niya is yung heat rejection. So the useful refrigeration is the heat transfer process 4 to 1. So underneath the area beneath line 1, 4 to 1. So the area under line 2 to 3 represent the heat rejected from the cycle. Under 2 to 3 is ipit to lahat. So the difference between the heat rejected from the cycle and heat added to the cycle is the net heat for which for a cyclic process equals the net work. The area enclosed in rectangle 1 to 3, 4 represents the network. An expression for the coefficient of performance of the Carnot refrigeration cycle is therefore as T sub 1 times S sub 2 minus S sub 1 yung entropy divided by T sub 2 minus T sub 1. Ito yung difference of temperature times siyempre yung difference of entropy is equal to T sub 1 over T sub 2 minus T sub 1. Okay. So, huwag natin i-discuss yung entropy, ano yung temperature, dumaan ka sa thermodynamics, meron na rin Carnot cycle doon. Di ba? Sa termo niya. Depending wala kayo ng termo sa termo to niya, meron niya. Now, the coefficient of performance of the Carnot cycle is entirely a function of temperature limits and can vary from 0 to infinity. Diba kasi na-cancel yung entropy. A low value of T2 will make the coefficient performance high. Yan. Pag mababa to, so tataas yung COP mo. Diba? Yan ka ng pag-analyze ng formula. Diba? Itataas mo to, siyempre bababa yung value ng COP. Diba? So alam niyo na kung bakit bumaba. Lumaki yun ng T2. Yan. A high value of T1 increases the numerator and decreases the denominator, both of which increase the coefficient of performance. So dalawang effect, di ba? Okay. The value of T1 therefore has a more pronounced effect upon the coefficient of performance and T2. To summarize, for a high coefficient of performance, one operate with T1 high and operate with T2 low. Ibig sabihin, pag pinagsama mo yan, ay ito, low yan. So, ang network mo baba. Okay. So, next, set natin itong Carnot heat pump. Sa application, bihira pa sa atin dito heat pump, pero sa mga water supply, sa hot water, ginagamit na ito. Pero bihira pa. Pero sa mainit na lugar, aircon cooling lang ang ginagamit. Sabing cooling heating, sa malamig na lugar, meron silang cooling heating. So, magagamit sila ng heat pump. A heat pump uses the same equipment as a refrigeration system, but operates for the purpose of delivering heat at a high level of temperature. Even though the equipment used in a refrigeration cycle and in a heat pump may be identical, the objectives are different. The purpose of a refrigeration cycle is to absorb heat at low temperature. That of a heat pump is to reject heat at a high temperature. So, yun ang purpose. Ang purpose naman sa heat pump is yung nire-reject ng heat. Yun ang ginagamit natin. A plant can be constructed to operate alternately as a heat pump and a refrigeration cycle. So, meron kang valvula na i-reverse mo yung direction. Hindi. Yung hangin. Units of this type are available for air conditioning, application of cooling a building during summer and heating it during winter. So yung hangin, siyempre, yun ang ano mo, to divert mo. The performance of a heat pump is expressed by performance factor. In keeping with the practice of defining the performance index as the amount of desired humidity divided by the amount of expenditure, the performance factor is equal to the heat rejected from the cycle divided by the work required. So the quantities of energy which make up the performance factor can be represented by areas of temperature entropy diagram of the Carnot cycle as in figure 4. So, ganun pa rin ang direction. So, the underline 2 to 3 represent the heat rejected sa ito. And the area enclosed in rectangle 1 to 3 represent the network. So, the performance factor is T sub 2 times S sub 1 minus S sub 4 over T sub 2 times minus T sub 1 times S sub 1 minus S sub 4 is equal to T2 over T sub 2 minus T sub 1. So the refrigeration cycle with the same temperature in figure 4 would have a coefficient of performance of T1 over T2 minus T1. Therefore, performance factor is T2 over T2 minus T1 is equal to T2 over T2 minus T1 minus T2 minus T1 over T2 minus T1 plus 1. So the performance factor vary from 1 to infinity. So the performance factor is equal to coefficient of performance plus 1. Take note, pwede rin kayong, this is, kung makita kayo sa ibang book o sa reviewer, makita mo to COP, cooling, may subscript na C, plus 1, is equal to COP, may subscript na H, that is heating. Yan. COP H is equal to COP C plus 1. So, yan ang sa iba. So dito sa case talker, ginamit niya is performance factor para maiba sa COP. COP kasi kadalasan isa refrigeration o sa cooling. Using vapour as a refrigerant. Ibig sabihin, so using vapor as a refrigerant or when a gas is the refrigerant kasi hawan, pasok ka sa gas. Yung actual na yung mga refrigerant na ganyan. So, ang tawag doon is actual cycle. Because the Carnot refrigeration cycle is the most efficient cycle, every attempt should be made to reproduce it with actual equipment. Certainly, the reversible processes cannot be duplicated, but at least the rectangular shape of the cycle on the temperature diagram should be maintained. Doing so means that all the heat can be received at one temperature level and rejected at another. If a gas, such as air, is used as the refrigerant, the cycle would appear as in figure 5 rather than as the rectangle of the Carnot cycle. This diagram is for air. This diagram. Air is a near as ideal gas. So 1, 2, 3, 4. Wala pa tayo sa refrigerant na merong doon, yung wet region. Iba yun. So the isentropic compression and expansion are processes 1 to 2 and 3 to 4 respectively. So this is for air. Later, meron tayong air cycle refrigeration. So babalik tayo dito. Okay. Processes 2 to 3 and 4 to 1 are constant pressure cooling and heating processes respectively. This cycle differs from the Carnot cycle operating between the same two temperatures by the addition of areas X and Y. At point 4, the temperature must be lower than the cold room temperature so that as the gas receives heat in the constant pressure process, it rises to a temperature no higher than that of the cold room. For similar reasons, T2 must be above the atmospheric temperature, and the effect of area X is to increase the work required. The effect of area Y is to increase the work required and to reduce the amount of refrigeration. Both this effect and Y both these effects of area Y reduce the coefficient of performance. Effect of area X and Y. Instead of a gas, a refrigerant may be used that condenses during the heat rejection processes and boils during the heat addition or refrigeration processes. So ito, ang advantage ng refrigerant. So this is in the wet region. Parang sa steam din, nag-umpisa tayo sa wet region. Carnot refrigeration cycle when a condensing and evaporating fluid is the refrigerant. Refrigerant na mga R12, the wet region. Air is also a refrigerant pero iba yung diagram niya. Ito yung mga common refrigerant: saturation, atmosphere, cold room. Such a refrigerant could therefore operate between the liquid and vapor states. With this refrigerant, the Carnot cycle can fit between the saturated liquid and saturated vapor line as shown in figure 6. Ito kasi ang purpose niya. Pagkakuha ng constant temperature. Process 2 to 3 and 4 to 1 take place at constant temperature since constant pressure passes in the mixture region proceed at constant temperature. Diba? Process 2 to 3 is a condensation process, and the vessel in which it occurs is a condenser. Yeah. Process 4 to 1 is a boiling process, and it takes place in the evaporator. Okay. Evaporation lang tayo. Pag sa power plant ang tawag doon is boiler. Diba? High. temperature is boiling. This is below cold room. The compression process 1 to 2 in figure 6 is wet compression because the entire process occurs in the wet mixture region with droplets of liquid present. Yeah. When a reciprocating compressor is used, several factors discourage the practice of wet pressure kasi may epekto sa compressor pag wet yung refrigerant. One is that liquid refrigerant may be trapped in the head of the cylinder by rising piston, possibly damaging the valves or the cylinder head. Even though the point at the end of the compression shown as point 2 figure 6 is saturated vapor and thus should be free from liquid, such is not the actual case. Pwede na hindi umabot. So, this is a constant entropy pa rin. So, later na yan discuss na muna. Wet compression, pataas. Yan. Wet compression versus dry compression. So, during compression, the droplets of liquid are vaporized compression by an internal heat transfer process which requires a finite amount of time. High-speed compressors are susceptible to damage by liquid because of the short time available for heat transfer. In a compressor that has a rotative speed of 30 revolutions per second, for example, decompression takes place in 1/60 seconds. At the end of compression, point 2 on the saturated vapor line represents only average condition of mixture of superheated vapor and liquid. Another possible danger of wet compression is that the droplets of liquid may wash the lubricating oil from the walls of the cylinder, accelerating wear. So because of these disadvantages, dry compression, which takes place with no droplets of liquid present, is preferable to wet compression. If the refrigerant entering the figure 7 is saturated vapor, kasi ito yung pinaka-minimum. Maging dry siya, di ba? So, pag lumabas doon, superheated na later. The compressor point from 1 to 2 is called dry compression. And this one is tawag doon superheat horn, sungay. With dry compression, the cycle loses the rectangular shape of the cycle. Compression of a dry vapor results in a temperature at point 2 which is higher than the condensing temperature. The refrigerant therefore leaves the compressor superheated. The area of the cycle which is above the condensing temperature is sometimes called the superheat horn. On the temperature entropy diagram, it represents the additional work required for dry compression. So magsasuffer to save the compressor. And yung disadvantages, may kapalit. O yung advantages, may kapalit siya. So, pero mas malaki yung advantage na ngayon. Pagkisa dito, sira yung compression mo, yung sa yan. So, dito, na problema, kunti lang naman yung area. Okay. Kasi pag may propose kang maganda sa bagay, mga tao, meron diyang mag-o-oppose. So, kung kunti lang, bali, wala mo yung oppose na yun. Kunti lang naman yung mas advantage na kumpara sa advantage na plano mo. Next, expansion process. Ito na tayo sa expansion dito po. Another revision is made on the Carnot cycle to alter the expansion process. The Carnot cycle demands that the expansion takes place asymptotically and that the resulting work be used to help drive the compressor. Help drive, so may ikabit mo yung turbine sa magdadrive sa compressor. Ito, di ba? Yan purpose. Practical difficulties, however, militate against the expansion engine. One possible work that can be derived from the engine is a small fraction of that which must be applied to the compressor. Two, practical difficulties such as lubrication include when a fluid of two phases drives the engine. Two phases, diba? Yun nga, with region. And three, the economics of the power recovery have in the past not justified the cost of expansion engine. Yun yun. So, malaki kasi yung engine. So, the necessity still remains of reducing the pressure of the liquid in process 3 to 4. A throttling device, such as a valve or other restriction, is almost universally used for this purpose, barring changes in potential and kinetic energy, and with no heat transfer of heat, S3 is equal to S4, and that is, the process is isenthalpy. Now, the constant enthalpy throttling process is irreversible. And during the process, the entropy increases. So the throttling process takes place 3 to 4 in figure 8. So, ibig sabihin, irreversible, pwedeng pa-iba siya. Pero consider lang natin as an average. So, irreversible. Irreversible kasi 3 to 4, 3 to 4, ganyan pala yung itsura niya. It's not irreversible. So, dito H3 is equal to H4. So, meron siya enthalpy. So, dito na derive yung standard vapor compression cycle. The standard vapor compression cycle is shown on the temperature entropy diagram in figure 8. The processes constituting the standard vapor compression cycle are 1 to 2, reversible and adiabatic compression from saturated vapor to the condenser pressure. 2 to 3, reversible rejection of heat at constant pressure, causing the superheating and condensation of refrigerant. 3 to 4, irreversible expansion at constant enthalpy from saturated liquid to the evaporator pressure. 4 to 1, reversible addition of heat at constant pressure causing evaporation to saturated vapor. Next is the properties of refrigerants. So, dapat marunong ka magbasa ng properties of refrigerants. Meron ng refrigerant properties table, di ba? Marami yan sa mga libro, sa likod, pero ng buong libro, puro properties lang. So, same lang ng pagbasa ng state tables. So, the pressure enthalpy diagram is the usual graphic means of presenting refrigerant properties. Yan. Yan yung minsan sa problem solving, gagawa pa PS. Hinahanap is PS dapat. Madali ito. In other thermodynamic work, the temperature entropy, pressure volume, or enthalpy entropy diagram may be more popular. In refrigeration practice, the enthalpy is one of the most important properties sought, and the pressure can usually be determined most easily. Dito, nga PS. A skeleton pressure enthalpy diagram is shown in figure 9. So the pressure is the ordinate and the enthalpy is the abscissa. Ordinate y-axis. X-axis, abscissa is the enthalpy. With the saturated vapor and saturated liquid lines as the reference, saturated liquid, tapos ang critical point, saturated vapor, complete line. Lines of constant temperature, ito, bago mag-saturation. Yan. So, ito. This is not actually vertical. Entropy entropy ito S, constant. Yan. Maganon. Sa labas. Entropy. And specific volume. Yan ang linya. Pag gumawa kayo ng sketch, yan. The constant temperature line is horizontal in the mixture region because here the temperature must correspond with the saturation temperature pressure. The subcooled liquid or compressed liquid region is to the left of the saturated liquid line. Yan, ang tawag dito is subcooled if it is temperature based. Compressed liquid if it is pressure based. Diba? So, paras lang yan. In this region, the constant temperature is practically vertical. The temperature, so yan. Kaya pwede mo yan. Pag may temperature ka, so makuha mo na yung pwede mo kang gawin gamit yung saturation. Isang enthalpy niya parehas. Okay. Pressure. Yan. Yung iba, temperature, kinukuha niya ito. Na-assume niya kasi malapit lang naman yung enthalpy. Pero pag meron kang pressure temperature sa steam, so gamamit ka ng compressed liquid properties kasi may table na available. So dito sa refrigerant, use lang ng S of F niya. S of F, saturated liquid enthalpy. Now, the temperature of a compressed liquid therefore determines the enthalpy and not the pressure. Diba? Temperature, kung naming S of F, yun na. At any pressure, basta may temperature, subcool. Siya yung enthalpy niya. So this statement conforms to the standard practice in using steam tables at moderate pressure. So to find the enthalpy of liquid water that is subcooled, the enthalpy is read as the enthalpy of saturated liquid at the existing temperature, even though the actual pressure is higher than the saturation pressure. The superheat region is to the right of the vapor lines. Ito, superheat. Itong part na to. In the superheat region, the lines of constant temperature becomes vertical. Ulit. Delta S is constant times delta T. Typical relationship of enthalpy and temperature of perfect gas. So the lines of constant specific volume slope upward to the right. Yeah. Lines of higher specific volumes are found at progressively lower pressure. The lines of constant entropy runs upward to the right, are reversible in adiabatic compression, which is asymptotic, shows the expected increase in enthalpy as the pressure increases during the compression. So dito, diba, tumaas siya. Compress ka. So, ibig sabihin, tataas yung entropy mo. Magkakaroon ka ng isang line dito. So, magkakaroon ka ng entropy difference. Next, pressure enthalpy charge for the superheated region of ammonia, refrigerants 11, refrigerant 12, refrigerant 22, and refrigerant 502 are available in temperature. Others, mga new refrigerant 134, 410, available na rin yan doon sa mga manufacturer. Okay? Online, marami yan. So, kung pwede kaya mag-download ng tables and charts. Tabular property data are also available. Refrigerant 22, for example, is the generic name for refrigerant that is marketed under such a name as Freon 22 and Genetron 22. Ammonia is the refrigerant used in an industrial refrigeration system. A more thorough comparison of various refrigerant will be found in the literature. So note sa pagbasa ng refrigerant properties, yung isang reference lang. Sabihin, pag R22, refrigerant 22, yung saturation properties Saka yung superheated properties, isa lang ang gamitin mo. Kasi meron isang libro na nangyari nun, yung ito yata sa, sa Stoker, yung meron siya tabulated na saturated properties. Pero yung superheated na graph. Kaya ginawa ng estudyante, doon sa isang libro, merong tabulated properties yung superheat, doon siya kumuha ng value. Pero yung saturated niya, doon sa, dito sa stoker. So, balik tayo sa solusyon niya. Okay? Ito yung example. Ito naman yung sample ng chart. Diba? Pressure, enthalpy. So, kayo pagbasa nyo, yung tingnan lang ng mata, gumamit kayo ng roller, yan. Tapos, kung ito log scale, natutunan kayo magbasa ng logarithmic scale. Diba? This is 1. Then, ito parehas. Then, so, meron itong this is 0, magiging this is 8. Di ba makita niya pa yung 10 sa kawan, tapos pares na yung labas niya. So, this is a logarithmic scale. So, para ma-convert mo siya sa linya, so this is magiging 0. Eh, natural log mo lang, 0, this is 1. Pwede ka na mag-interpolate yan. Natural log mo to, 0 to 1. Tapos, pag nakuha mo yung value doon dito, tama, ito ka naman pagkukunin mo yung value dito. So, yung linear mo ang gamitin. Ma-interpolate mo siya. Ma-ratio mo. Makuha mo yung value, tapos i-untitled. Ano mo, yung natural log mo, ln, ano mo yun, i-inverse mo yun. So, e-exponent, kung anong value mo dito, makukuha mo yun. Ano dito, value. Bar. Yan. So, tinuruan siguro sa inyo yung ano. Sana tinuruan kayo na magbasa ng chart, mga graph na logarithmic scale para mag-ano kayo sa pag-interpolate sa graph. So, yung line nyo dapat straight din dito. Okay? At huwag nyo lang i-drawing yung graph. Mga ganitong graph, huwag yung i-drawing. I-dikit nyo lang doon. Copy-paste nyo o i-dikit nyo sa solusyon nyo. Kung nakalagay sa solusyon nyo, require na ilagay yung figure, yung chart, huwag nyong i-drawing. Okay? Kasi masisira yung distansya niya. Okay? Iba ang dami. Lahat tinurowing. So, ayun, kasi riro. And then, ito sa table, simple interpolation. Okay na? So, what would be the appearance of the standard vapor compression cycle on the pressure enthalpy diagram? Figure 10A, so ito, shows the processes which constitute the cycle. And figure 10B is the schematic diagram of equipment or the flow diagram. Tama ba direction? Tama yan. 1, pasok sa compressor. 2, 3, 4. So ito na, 1, 2, 3, 4. Yan ang ano niya. So umpisa natin, ano na, di ba? Dito ang 1 yata sa kato. So pagdating sa pH na, ito na yun, 1, 2, 3, 4. Kasi mag-start siya sa compressor. So ito na gamitin natin. Pwede rin gamitin yun, basta yung solusyon nyo, sumusunod din sa number. Yung number no, sa solusyon, sumusunod sa figure. Okay? So baka ito, palitan nyo ito ng 1, 2, 3, 4. Yung solusyon mo, yung H1 mo, dito nakalagay. Pero yung number mo na 1 nandito. So mali ka pa rin. Diba? Kasi mayroong ano, ito, may figure to, may figure to. 1, 2, 3, 4. Tapos dito, 1, 2, 3, 4. So mali tayo. Sa figure pa lang mali na. So sayang yung mga solusyon mo. Diba? Kaya nga, ni-require ko yung figure para makita kung naintindihan nyo yung ginagawa ng solusyon. Okay? Kaya mag-ingat sana pagkopya. Kaya kinopyahan mo mali, so lahat kayo mag-ingat. Okay? So, process 1 to 2. This is compression, isentropic compressions along the constant entropy line from saturated vapor to the condenser pressure. So process 2 to 3 is the constant pressure, the superheating and condensation, which is a straight line on the pressure enthalpy diagram. The throttling process 3 to 4 is one of constant enthalpy and therefore is vertical on the chart. Finally, evaporation process 4 to 1 is a straight horizontal line because the flow of refrigerant through evaporator is assumed to be at constant pressure. Assumed to be. Meron tayong later naman is yung mga actual pressure. Okay? With the help of the pressure enthalpy diagram, the significant quantities of the standard vapor compression cycle will be determined. So the quantities are the work of compressions, the heat rejection rate, the refrigerating effect, evaporation, the coefficient of performance, the volume rate of flow per kilowatt of refrigeration, and the power per kilowatt of refrigeration.